Okay. So this is the only topic which is left in the forming syllabus. So today we will cover this topic and we will also look for powder metallurgy. Then your full metal forming will be completed. So what is drawing? So drawing is a plastic deformation process in which a flat sheet or plate is formed into a three-dimensional part with a depth more than several times the thickness of the metal. So what happens in this process? A punch will be set into a die, and that your metal, your blank will take the whatever the configuration which is provided on the die. So this is the drawing process. So this is the diagram for the drawing process. This these are things we already know. This is called punch. This will be your blank, your sheet, and this is your die. And there will be one blank holder will be there to provide some holding force because there is a need to hold the blank. So there will be a blank holder through which we will provide some holding force to the blank. So this is your assembly for drawing. Then there are again cold drawing and hot drawing. So hot drawing is used for the thick walled parts of simple geometries where what we are doing thinning process will take place. And in cold drawing there will be thin metal and there will be very less or not at no change in the thickness. And in cold drawing we can produce a wide variety of shapes. Then the blank size. So this is one relation in between your blank and your drawn cup. So this relation actually comes from the what the condition. See, the surface area of this sheet or this blank will be equal to the surface area of the cup which is being drawn by the process. So suppose this was your round blank. This formula is for round blank, but the general formula will be surface area of blank will or should equal to surface area of cup. So suppose the diameter of your blank is capital D, then the surface area, what will be the surface area? Surface area will be pi by 4 capital D square. Then surface area of the cup. So the area of the this much will be pi by 4 small d square, and then the area of the walls will be pi dh. When you will solve this, you will get this formula only. Then it will be d square is equals to small d square 4 pi 4 dh. Then d will be under root d square plus 4dh. So mostly in the question what they will ask you, they will give you the cup diameter and the height, and they will ask you what should be the blank size. So if it is a round blank, if it is a round blank, then directly you remember this formula, you apply the formula and you get the answer. Most of the question you will get round blank only. If the blank is not round, suppose this is of this kind of sheet or something, and from that you are making a rectangular cup, then you have to use this condition that the surface area of your blank will be equal to the surface area of your cup. Okay. Try to solve this question now.
Blank is the initial sheet we had, right?
Yeah, blank is initial workpiece, whatever you have. Try to solve this question.
See, ma'am.
Yeah, option C is correct. So let's read this question. For obtaining a cup of diameter 25 mm and height 15 mm. So there will be a blank, and then with the help of that blank you are making a cup. So diameter of this cup is small d, which is given as 25 mm, and the height is given as 15 mm. The size of the round blank should be, and they are asking what is the size of this blank. So the formula we already know, that is capital D is equals to small d square under root 4dh. So here we can write it as 25 square plus 4 into 15 into 25. When you will solve this, it will be 5 into 17 into 5. It will be 46.09 mm. So your option C will be correct. Any doubt in this question? Fine. Now try to solve this question. Okay, one more thing which is written in this slide that we should discuss. So this formula is applicable when D is greater than 20 R. What is R here? R is your corner radius, which is this radius. So in corner also we will provide some radius which is called as corner radius. So suppose your corner radius is following this condition, that is D is greater than 20 R. So directly you can use this formula. Otherwise you have to, otherwise if it is very small then we don't have to consider it. But suppose if your radius is a little bit large, then we have to consider it in some, it will take some material also, right? So we have to consider it in the surface area. So if your condition, if it is following this condition, that is D is greater than 20 R, then you have to use this formula. Then you do need not to worry about corner radius. But suppose if your corner radius is following this condition or this condition, then your formula will be changed by these two formula. Your formula will be replaced by these two formula. That also you should remember. Okay. Now try to solve this question.
Madam,
Yes.
in questions they will provide us R.
Yeah, if they want you to use this like this question only. Here they are providing corner radius is given. When the corner radius is not given, that means you don't have to think about that. You don't have to use that. So here it is given. So first you have to check what condition it is following. You read the question, write the data, then I will go back to formula slide again. Okay, now try to solve this question. Hello.
Yes.
Well, madam, here is also first formula, I think.
Yeah, here you have to use first only.
C.
Yeah, C is correct answer. So in this, just to confuse you, they have given the corner radius. So firstly, what we have to find? We have to find 20R. If you'll do 20R, that is 20 into zero point 0.4, so it will come 8. So you can use this condition, that is D is greater than 20R. So if you'll use that condition, you have to go with this formula only, that is D is equals to under root small d square plus 4dh. So when you will put the values, it will be 100 root 5 then it will come around 22 to 3.60 mm. So your option C will be correct. Any doubt in this? Okay. Yes.
No, ma'am, no.
Yes. Okay. Now try to solve this question.
Twenty-eight point seven two ma'am.
Yeah, correct. 28.77.
7.
Okay. So let's read this question. A 10 deep cylindrical cup with diameter of 15 is drawn from a circular blank. Neglecting the variation in the sheet thickness, the diameter up to 2 decimal points accuracy. So again we have to use this formula only, that is capital D is equals to small d square plus 4dh will be under root 15 square plus 4 into 10 into 50. You will get around 28.72 mm. Any doubt in this question?
No.
Okay. Now tell me the answer of this question.
A.
A. A is the correct answer. Okay. Then, so this is just a formula based question. So you should remember the formulas. Now, this is the formula for the drawing force. Suppose what sometimes they can ask about the uh, drawing force, where C is your clearance, and capital D and small d we have seen in the figure. T is the thickness and sigma is the average stress. Then one more term which is required is blank holding force. So blank holding force required depends upon the wrinkling tendency. So suppose if you are not providing enough blank holding force, or you are providing more than the required blank holding force, then there will be defects that will be generated in your cup. So that is why blank holding force is required. And there will be clearance between your die and your punch. So in the drawing, your clearance is defined as punch diameter is equals to, this is how you calculate the punch diameter, that is die opening diameter minus 2.5, and T is the thickness of your sheet or blank. Okay. Then now move on to deep drawing. So it is like a drawing process only, but in the deep drawing process, when the cup height is more than half the diameter, then it is termed as the deep drawing. And this forming process is being used for ductile material because it is easy for the ductile materials. Now, one more thing that we should know, what kind of stresses that will be generated in your cup during the deep drawing process. So in the flange, this is your flange. So there will be tension also and compression also. This is your flange. You are compressing it also, and there will be tension force also, right? Because you are stretching it. In your wall, there will be only uniaxial tension because you are stretching the wall. So this is your deep drawing process, and whatever the stresses which are formed in your cup during the deep drawing process. Then one more term is there, deep drawability. So the ratio of the maximum blank diameter to the diameter of the cup drawn is known as the drawability. Then there is one more term which is known as limiting drawing ratio. Suppose there will be a draw ratio. Otherwise, if you are not, if you are going beyond your drawing ratio, if you are crossing the limit, it will uh, it will start blanking. It will start piercing or blanking. It will not draw the product. So for that, we have to keep these things in the mind. First is drawability, and second is limiting drawing ratio. After which the punch will pierce a hole in the blank instead of drawing. So this ratio is basically depend upon the material and amount of the friction that is present during the drawing process. So generally what limiting drawing ratio is acceptable, that is 1.6 to 2.3. Next, this is with the help of the limiting drawing ratio, you can calculate the average reduction in deep drawing. So suppose what is the formula for the reduction? That is 1 minus limiting drawing ratio multiplied by 100. So with that, suppose if your small d by capital D is zero point 0.5, so in one go you can reduce up to 50% only. The maximum reduction will be up to 50% possible in the first draw. That is how you calculate the average reduction, and that is why limiting drawing ratio is important. If you will try to reduce it, will if you will try to change more than 50%, beyond the 50%, suppose you can reduce up you can increase up to some height, suppose 10 and if you will try, which is under the limit, but if you will try to go beyond that, which is not coming under your limit, under your drawing ratio, then it will form a hole in that. It will start piercing instead of drawing. So that is why this is also important. Now, these are very important things for deep drawing, that is defects. So defects in drawing, first is wrinkle. Suppose your blank holder, there will be one blank holder by which you are holding your blank, or the first product workpiece by which you are holding your blank. So suppose it is not it is insufficient, it is not the appropriate, so it will cause wrinkles. It will cause a wrinkle in your flange also, and it will cause wrinkles in your wall also. Then second is fracture. Suppose your blank holder pressure is too much, that your material is not able to draw, so it will fracture at some point during the corner or maybe on the walls. So when your blank holder pressure is higher than required, then it can cause fracture, and if it is insufficient, then it will cause the wrinkles in your flange and walls. Then one more important defect is earring. Earring actually forms because of the if the anisotropy is present in your material. Okay. One otherwise, suppose you are not providing sufficient or proper blank holding pressure. Suppose somewhere pressure is higher, somewhere pressure is lower. So somewhere it will draw more, somewhere it will draw less. That can also cause the earring. But the main reason for earring is anisotropy of the material. Suppose if your material is not anisotropic, it has a uniform properties, but still earring is happen. That means somewhere your blank holding pressure is not proper, or maybe you haven't provide the proper clearance if the earring is forming. Then okay, now try to solve this question.
B, ma'am.
Yes, B is correct. So as we have seen previously that why earring is directional. It is mostly because of the material properties. But if you are not providing uniform blank pressure, if your blank holding is not uniform, if the clearance is not proper, then also earring can happen. So your option B is correct for this question. Yes.
Speed of the press doesn't come into the picture, is it? Because if the speed is more, probably the force will be more.
How is that depend upon the speed? No, it will not depend upon the speed.
Okay.
Okay, because uh, for blank, mostly you're providing more force on the blank only. You're trying to you're more focus on your blank holder. See, your force will be more than the your force will always be less than the whatever the blank pressure we are providing, right? Otherwise, uh, blank is suppose you are holding, and whatever holding force is required is your blank pressure, and whatever the force you are providing to do the drawing process, it will always be lesser than the your blank pressure, right? It should always less than your blank pressure, otherwise your blank will move down. Okay,
Fracture will occur.
sorry.
Fracture defect may occur.
It may occur, defects may occur, and it will may go down also. So that is why what we do generally, the force will always lower than your holding pressure. So that is why our prime focus will be the holding pressure. So that is why your speed will not affect, it will cause it can cause a defect but not the airing one. Okay. Okay, this is one more defect that can form during drawing, that is misstrike. Suppose there will be some slight of misplacement of the stock or your blank, then your flange will be unsymmetrical. So this defect is known as misstrike. Then the orange peel. So orange peel is what? A surface roughening defect. So it happens because of uneven flow, or you can say suppose your material is having um, large grains. Suppose you're doing deep drawing after annealing process, so there will be large grains, so that is why some surface roughening will be present after the drawing process due to coarse grain size, so that is called orange peel. Then scratches. Suppose your die or punch is not having smooth surfaces. Suppose your die is having some kind of small impressions on that. So because of that, if your surface or some roughness is there, so because of that also some scratches can form on your blank or cup. That is this kind of defect can also be formed in drawing. That is known as scratches. Now try to solve question whatever we have seen till now.
A.
Yeah,
A.
correct. A is correct. Let's read the question. In the deep drawing of cups, blanks show a tendency to wrinkle up around the periphery. So when wrinkle form, when there will be a insufficient blanking press. So because of that, there will be a buckling on the circumference due to the compression. Okay. So in the option, there will be one cause and there will be one remedy. So what is the remedy? How we can reduce this defect of wrinkle by increasing the blank pressure. So option A is correct. That is buckling due to circumferential compression, and increased blank holder pressure will be the remedy for this defect. Okay.
Madam, C is also same.
Sorry.
C also looks correct.
Yeah, C also looks correct. See, but you cannot go to very high temperature for drawing, right?
Yes.
And when you're if you're doing suppose if you're doing hot drying, then you don't have to put coolant in that, right? If you are going for a very high temperature, then it will be hot drying. In hot drying, you will not provide the coolant, right?
No, I thought again and again by using that punch,
Okay,
it
okay,
may get hot.
okay. It will not get that hot. Okay. During the piercing process or blanking process, when shear stresses are present, then there are very high chances to increase temperature up to limit so that your material start expanding. But during this kind of processes where shear stresses are not present, there will not be those temperature increase will not be that sufficient to form that kind of defects. Now move on to this one more process, that is spinning. This is a very easy process, as you can see in the drawing picture. Spinning is a hole forming operation in which a rotating disc of sheet metal is shaped over a mandrel. So there will be a localized pressure which will be applied through a simple rounded end wooden or a metal tool. So there will be a rotating sheet metal, and there will be one mandrel, and mandrel will having the configuration, the shape, whatever the shape we want for our end product, and that mandrel will start pressurizing your sheet from one point, and it will produce the shape, whatever shape we want. Suppose this is our blank, this is our sheet, and we want this shape. So whatever the shape we want for our cup, or suppose here it is like that, here it is like that, whatever shape we want, that kind of shape we will use as a mandrel. Then this is some theory for spinning process that I think is not important, but you should read. I will upload the notes from which I have taken all these slides. So you should go through from that notes also. Uh, I have prepared from these notes, so I'm using these notes. One more process is there, stretch forming. So, stretch forming is actually to produce large sheet metal parts for very low or limited quantity. In this, what happens? There will be a sheet metal which is gripped by two or more sets of jaw, and uh, what we are doing, we will stretch the sheet from one or both the side. So in this, the deformation, whatever the deformation will be induced, that will be induced by tensile stretching, and the forces on the form block are far less than those normally encountered in the bending. So this is not bending, this is stretching, because the force, whatever will cause the shape change, that will be lesser in the whatever compared from the bending or forming. So when the force is also less, there will be less spring back effect in this process, and it is used for low melting point of metal or for plastic also. So this process is very useful to make the body for aircrafts or automobiles. Suppose your windshield or your door panel or your car panel, this kind of like sheet metal process, they use stretch forming. And this is the diagram. There will be one jaw, and they will your blank will be gripped in between these jaws, and one there will be one what you can say blank uh, through which you will apply some pressure, and there will be completely tensile stresses generated in your blank, and it will stretch in required dimension. So this is the important formula. So suppose there is a biaxial stretching. This is your sheet. You are stretching from this side also and this side also. So this is the uh, strain in the first direction. Suppose this is your first direction, and firstly your dimension was L01. This is your first direction. This is your second direction. Firstly, your dimension was L01. Now it is Li1. So this is the strain after in the first direction, this is the strain after second direction. So how the this is affecting the thickness, that is this direct formula for the final thickness, that is initial thickness divided by e to the power epsilon 1, that is strain 1, and e to the power epsilon 2, that is strain 2. So you write this formula and then we will solve one question on this formula.
Ma'am,
Yes.
This is engineering.
bending stresses, only tensile stresses are along with bending stresses also induced.
Only this is stretching. We are not bending, we are just stretching. So only tensile stresses will be present during stretch forming. Okay. Okay. Now try to solve this question.
Okay, can you go back to previous slide for me?
Sorry.
Yes, ma'am, just a minute. Yes, ma'am, thank you.
Solve this question.
B, ma'am.
Option. You tell me the answer.
B, ma'am. B, B. B, ma'am.
Option B is correct. So let's read the question. A 1.5 mm thick sheet is subjected to unequal biaxial stretching, and the two strains in the direction of stretching are 0.05 and 0.09. That is, your strain 1 and strain 2 is given. The final thickness of the sheet in mm. So your final thickness is T, that is 1.5 mm divided by e to the power 0.05 to e to the power 0.09. When you will solve this, it will come as 1.304 m. Okay. Now move on to this one more process, ironing. So ironing is what? It is the process of thinning the walls of a drawn cylinder by passing it between a punch and die whose separation is less than the original wall thickness. So what is happening in ironing? You will have one deep drawn cup. There will be a cup. Now you want to reduce the thickness of the walls only. You don't want to reduce the thickness of your uh,
Base.
base. Yes. So thank you. So you don't want to reduce the thickness of your base, you want to reduce the thickness of the walls. Then this is the process that is called as ironing. So what you do in the ironing, uh, you pass your drawn cylinder between the punch and die whose clearance or separation is less than the original wall thickness. So this is the diagram for the ironing. So in mostly in the paper, one kind of question they can ask from the ironing, that what is it ironing? So that you should know, which is important. You should know what is ironing. Then a few more process like embossing. So with the help of this process, you can make embosses on your sheet metal by this kind of process.
This ironing and deploying is
Sorry.
this ironing and deploying is same.
Ironing and deploying is not same. cup which is made by deep drawing. So whatever the thickness of your base and whatever the thickness of your wall, which that will be equal. So have you seen that cans like Coca-Cola cans or
Yes, ma'am.
huh. So in that you have seen that your base is having higher thickness than the thickness of your walls. So that is actually made by ironing. So firstly, what will do? They will make a small they will make a can by deep drawing. After that, they will they will do the ironing process. They will do the ironing process. With that ironing process, they will reduce the thickness of the uh, your deep drawn cup, and the wall thickness will be decreased and height will be increased. So that is high. One more this kind of question they can ask. Suppose they can ask that can or collapsible cans can be made of which process, then you have to know that it is made by ironing. So that is the main difference between the ironing and deep drawing.
But can it be followed by deep drawing?
See, what is deep drawing? Deep drawing you will get one blank, and you are making, suppose it is a circular blank, and with the help of that sheet you are making a cup. That is drawing. If your height is greater than 2 times of diameter, then it is called deep drawing. So that is the drawing process. Ironing process is what your one drawn cup is there, and you're reducing the thickness of that cup. That is already a cup that is already formed in a shape. Now you're giving another shape, or you're reducing just the thickness of the wall.
Okay, so the initial product is already a cup, so we are just reducing the dimension.
Yes.
Yes.
Madam,
Yes.
LPG cylinders are made by deep drawing.
We can make LPG cylinders by deep drawing.
No means what by what which process they are made.
Which
मैम
process?
डीप नहीं होती है, वो बीच से दोनों को ज्वाइन किया जाता है, तो डीप ड्राइंग तो नहीं है मैम, क्योंकि हाइट इतनी ज्यादा नहीं है डायमीटर कंपैरिजन में.
See, few parts can be made by deep drawing. Suppose uh, yeah, he's correct only. We cannot make it by deep drawing because we will connect because your bottom part will have a different dimension. Your how your cylinders looks like that, because your or
और
maybe
बीच से ज्वाइंट
maybe
होते हैं.
maybe I don't know about that cylinders. LPG cylinders. I will check. I don't know about LPG cylinders, how we make LPG cylinders. I will tell you in the next class.
Okay, ma'am.
Okay, then this is one more process, that was embossing, and then coining. Coining is actually a cold forging operation in which material will flow, but the flow will occur only at the top layer. So coining is used for making the coins. Whatever the impression that is made on your coin, suppose this is your coin, it will be first a small disc only, and with the help of coining process, there will be one punch. On punch, there will be impressions. Whatever the impression that you want to be. You want to be print on your coin or your disc, that will be present on the punch on other direction, and when you will press it on your disc, your material will start flowing in the whatever the impression that are being formed on your punch. So this is basically a forging process, coining. Then the bending is important. So suppose you have done your other sharing operation, so now we will go for the bending. So bending is depends upon the material properties, at what location you have to bend, and in your bending, at the bend there will be a biaxial compression and biaxial tension. Can you tell in which part there will be biaxial compression and which part biaxial tension?
Upper part tension.
Correct. In this part, it is there will be biaxial tension, and this part there will be biaxial compression. So this is you should there is one important formula for bending, in which they ask question about, that is bend alloy. So what is your bend alloys? That is alpha r plus kt, where r is your bend radius, alpha is your bend angle, and k is a stretch factor constant which depends upon the bend radius and the thickness of your sheet. If your bend radius is greater than 2t, then your k will be 0.5. If your bend radius is less than 2t, then your k will be 0.33. So write this formula, we will solve one question on this. Okay, then one more.
Previous, before previous,
Sorry.
previous slide.
Okay, this is one more formula for the strain on the outermost fiber of the bend. That is 1 upon 2r by t plus 1. So you should know this formula also. Then if you have written the formula, please try to solve this question.
C.
Yeah, option C is correct. Let's read the question. A 2 mm thick metal sheet is to be bent at an angle of 1 radian with a that one more thing that you should remember, that in this formula you have to use alpha only in the radian. Then let's go back to the question. A 2 mm thick metal sheet is to be bent at an angle of 1 radian with a bend radius of 100 mm. If the stretch factor is 0.5, the bend allowance is. So your alpha is 1 radian, R is 100 mm, K is 0.5, T is 2 mm. Then bend allowance is alpha r plus kt, will be 100 plus zero point 0.5 into 2. And you will solve this, it will come as 101 mm. So option C is correct.
Ma'am, in the figure, can you tell which length is the bend allowance?
Sorry.
Length is the bend allowance.
Can you please say again?
Which length is the bend allowance?
Okay. This length is the bend allowance.
Okay.
Ma'am, just one more thing. In the stretch forming, actually, we got L01, L1, that those four notations were there. It was. Can you kindly explain those four? Yes, these four lengths.
This is initial upon final only. The way we calculate the true strain, what is happening here, there will be suppose there will be a sheet, and you're stretching it in this one direction, and this is your second direction. So whatever the dimensions are changing, you have to just calculate the strain in this direction, one direction, and this is the strain in the second direction. So it is increasing. So what will be the formula?
Final upon it.
Final. It means I is a final, right?
Yes, this is final upon initial.
Yes, ma'am.
Okay. Okay, now try to solve this question.
D, ma'am.
Yeah, option D is correct. So let's read the question. Match the correct. So in the blanking, see whatever the material removal processes are there, shear stresses are responsible for material removal. So P will be 3 that we can write. Then stretch forming, I have told there will be only tension. So Q will be 1. Then next is coining. Coining I have told forging process. Forging means compression. So R will be 2. Then S is deep drawings. In deep drawing, there will be tension and compression. On which part tension and compression both will present? Can you tell?
Tension in the wall and the compression in the flange.
Yeah, but in the base, tension and compression both will present, right? So your S will be 4. So your option D is correct here. Okay, try to solve this one also.
A.
Yeah, option A is correct. So for coining, there will be compressive. Then the wire drawing. Wire drawing will be tensile and compressive. Sorry. Wire drawing will be, tell me,
Tensile only.
Tensile.
tensile only. Then next is blanking. Blanking will be
Shear.
shear. Then deep drawing will
Shear.
be tensile and compressive. Okay. Now solve this question.
B.
Yes, B is correct. So we can suppose if you don't know what is molded
Ma'am,
luggage. Yes.
ma'am, why won't it be like like moldage luggage should be injection molding as well now, ma'am?
See, suppose you have confusion for molded luggage, but if we'll go for others also, it is quite clear for these three, right? You can easily select what will be the process. So if your three are matching, then you can select what is the answer, right? So long structure, see, let's go with the very easy for very easy. So long structural shapes that will be made by hot rolling that we know. That is the easiest one here. So firstly, we'll go with the R, that is 2. Then the collapsible tubes that I have told you that will made by impact extrusion that we have studied, right? That also we can go. That is also easy. So in this question, for this question, with the two options also, if you will get correct, you can write the answer. Molded luggage is why it is not for other molding process, that I don't know, that I will tell you later. I'm writing it down. But this is a easy question, because if you there are three easy options for to solve this question. If you'll get three options correct, even two, if you'll get correct, you'll get the answer. So these are the easy ones, and move on to the tubes, packaging containers for the liquid. That also we have studied in the blow molding process, that is made by blow molding process. That also you can write easily. Then only P is left and only one option is matching.
मैम
Then
कोलैप्सिबल ट्यूब इम्पैक्ट एक्सट्रूजन होता है, इनडायरेक्ट एक्सट्रूजन होता है?
impact extrusion.
मैम उसमें क्या होता है?
See, those your tubes which are used for like toothpaste and all, that all are made by impact extrusion. We have seen all these, right, in extrusion class.
देखा था जहाँ तक याद है।
Okay,
मैम आई विल।
okay, okay. So your forming is finished. There are a few more questions that we can practice on forming. Now one more topic which is added in GATE is powder metallurgy. So in powder metallurgy, what we do, we will our metal will be in the powder form. Our metal will be in the powder form. Then we will, uh, with the help of this powder only, we will make our end product. So how will we do that? So in the powder metallurgy, as the name given, in this process, fine powder materials, firstly it will blend, then it will press into the desired shape or compact. This process is called as compaction. And then it will be heated. That process is called as sintering in a cold controlled atmosphere to bond the contacting surfaces of particles and establish the desired properties. So in this powder metallurgy, your workpiece will be, your first product will be a powder of the metal. Then what we will do, you will blend it into fine particles or whatever desired dimension is required. Then we will press it. Then we will shape in whatever the shape we want, we will press that in that shape. Then we will provide some heat to achieve the bonding between the particles. And that is how then we will press, and that is how we will find the end product. That is your powder metallurgy. So your first process is manufacturing of powder. So how we make, firstly with the help we what we will have after casting, suppose you got a ingot. So with the help of that, how will we make the powders? So your first process is atomization using a gas stream. Okay, this is whatever in next few slides we will read. That is the different processes to manufacture the powders. So first one is atomization using a gas stream. So what is atomization? Can anyone tell?
In small droplets.
Yeah, in suppose there is a stream of liquid, then you will divide that stream into very small droplets. So atomization is a process in which your molten metals are broken into small drops of liquid by high speed of fluids. Okay, this is the first. You should in the powder metallurgy, at least you should remember the name of the processes. So first is atomization, in which this is a process of molten metals are broken into the small drops of liquid, and then those small droplets will be heated, and that's how you will get the metal powder. Okay, tell me the answer of this question.
Yeah,
A.
ma'am.
A, correct. Then next, second is reduction. Reduction is also a process to produce the powder. So what is reduction here? Metal oxides are turned to pure metal powder when exposed to below melting point gases, results in a product of cake of sponge metal. So reduction process we have seen in the chemistry, it is somewhat like that. It is based on the principle what we do when you the pure metal will be exposed in some temperature which will be below the melting point of the gas. That will result a cake of or a spongy metal. With that sponge, the particles will be very soft, and you can easily compress that sponge like particles. So in this with the help of this process, we make a spongy metal or cake of spongy metal. That is also a process for producing a first product for your powder metallurgy. So this process is basically used for iron, copper, tungsten, molybdenum, nickel, and cobalt. Then tell me the answer of this question.
B.
B, right? So this is also solved. Now, next process is grinding. In what happens in grinding? Then, in this metallic powder is nothing but the unburnt tiny chips formed during the process of the grinding. Suppose you got your workpiece, you want to make the powder, so you'll do the grinding. Whatever that unburnt and chips are formed, that we will use as the first product for our powder metallurgy. This is the third third technique. Yes, this is the third technique. Then the fourth technique
मैम,
is, yes,
विदाउट बर्निंग हाउ कैन दे बी सेपरेटेड? जनरली मतलब फायर तो उनमें होता ही है ना
grinding. में no, it's not necessary.
मैम, जो स्पार्क टाइप जो निकलता है वो जलते ही तो है।
Some chips will burn, not all the chips will burn, right? Most
मैम
of the chips will not burn. You will provide some coolant or something.
ओके मैम, ओके।
Okay. Next process is electrolytic deposition. This is used for iron and copper. This is same like electroplating. What we do in electroplating, there will be one anode which will be deposited on the cathode material. Same process in this also. So what we do, suppose we are making a copper powder, so there will be copper plates which are placed in a tank of electrolyte as a anode, and there will be another metal that will be used as a cathode material, that is aluminum. So what we will do, when we will pass the DC current in our anode material, the copper will be deposited on the cathode material. So suppose this is your anode, this is your anode, this is your cathode, and this is your copper, and you want copper powder, and this is some any metal, suppose aluminum. So when you will then when the DC current will pass, there will be one electrolyte also. Then when the DC current will be passed, your anode material will start depositing on your cathode material. Then this plate you will take out, and you will scrap off the copper from this plate, and that is how you will get the copper powder. So this is one more technique for manufacturing of powder. So the cost of this process is very high, but you can get the desired grain size. Then some other techniques are also there that you should know: granulations, machining, milling, shooting, and condensation. Now solve this question.
B.
Compact test.
Yeah, B is correct. Which one of the following methods is not used for producing metal powders? So we have seen automation, we can produce metal powders, machining, grinding also, electrolysis also we can produce metal powders. Compaction is a different process, it is not being used to produce the metal powders. Now this is the overall chart for powder metallurgy. There will be one base powders, and we will use some binding material or lubricants. Then we will mix it. First process is mixing. Then we will press it, whatever the desired shape we want, we will press it in that desired shape. Then we will do sintering. Sintering is what? In a vacuum we will provide high temperature so that the bonding can happen. Then again we will press it. Then whatever the secondary option that is required, like machining, joining, impregnation, that we will do, and then we will get the final part. So this is the overall chart for powder metallurgy. Now yes,
No, ma'am. Blending operation.
Okay. Let's go first with the blending or mixing operation. So this is the theory that you should know. Mostly you should know the sequence for the powder metallurgy. And in some that I have written, what kind of lubricants, what kind of lubricant materials and binder materials that are being used, that also you should know. Then after blending or mixing, we go to compacting. What is green compact? Can anyone tell?
Consulting component without centering.
Yes, green means whenever this green word comes into forming, that means some moisture will present in there. Okay. So during compacting, your material will be very porous only. Porosity will be present, and it can be done as cold or warm. Then after compacting, we will do centering. Centering will be happen in no oxygen atmosphere. We will heat our material up to 0.75 times of the melting temperature. Then in this, your density will increase, your porosity will be reduced. Because of that, your strength will increase, brittleness will reduce because there will be bonding between the material, and porosity will also be decreased. Because of that, toughness will also increase. So this is your sintering process, in which density will increase, brittleness will reduce, strength will increase, porosity will decrease, and toughness will increase. All is related. So if you remember one, like density increase and porosity decrease, strength increase, you can learn others. Then try to solve this question.
C, ma'am.
C, correct, right? I think there is no second thought for this question. Now try to solve this question.
B, ma'am.
Yeah, B is correct. This is also we have just now seen. One
E.
more. Then one more process is there for pressing, that is cold isostatic pressing. So this is one process, one theory that you should remember, and then let move on to the features of the powder metallurgy products. So in the during after the sintering, then this process you can control the density or the porosity of your material, and due to that, your strength and hardness, ductility, all these things are controllable process. And you're pressing, so it will make it a better surface finish. Your surface finish will be good, and you will get the good accuracy dimension. Then these are some advantages, like good tolerances, surface finish. You can make complex shapes very quickly, and porosity can be controlled. There will be low waste, and automation of this process is very easy. There are so many advantages that you can read. Try to solve this question.
Powder metal.
Right. Then try to solve this question.
B.
B, ma'am.
B is correct. See, whatever the dyes that we are used in powder metallurgy, that are very costly. So, and it breaks easily when you are pressing. Like in our labs also, when we do compacting, when we are pressing, those dies can easily break, and those dies are very costly. So that is why overall the equipment cost for the powder metallurgy is high. So for this question, 1 and 2 is correct. So that is why there are some disadvantages. That is, your metal powders can deteriorate, like it can easily oxide will form, and impurities can be easily accommodated in your powders. Then fixing and setup costs are very high. Then the part size is limited by the press, and compression of the powder is used. Then suppose you're trying to make sharp corners, and if you want to make a wearing thickness, then this kind of requirement is hard to produce with this powder metallurgy. And suppose a non-moldable features which you cannot make by pressing. Suppose you want some what we can say, you want to make a cylindrical hole inside your product. So those kind of things are not possible for powder metallurgy. So this is for today's class, and I have this notes through which I have prepared uh, for metal cutting, metal forming. So I'm uploading this notes in the drive. What I suggest that you go through with these full notes and try to solve the question, whatever the questions are present. So if you're able to cover this full notes, then your most of the production part will be covered by this notes only. So in this, metal cutting, metal forming, and metrology are present. So I'm uploading these notes. You go through with these notes. I will also upload the short notes what I have. You can refer to that also. In the next session, we will start the welding and joining.
Madam,